So here we have the parabolic orbit, and that means that you end up actually parallel to this line when you get to infinity, which by that we can mean, let's say, 1,000 Earth radii. That's close enough to infinity for practical purposes. We will be parallel, this line will be parallel to this line, and v infinity, the speed that you'll have relative to the Earth, will be 0. If you launched a spacecraft with escape velocity and you got out to 1,000 Earth radii, your velocity with respect to the Earth at that point would be 0. And that means that you would be in an orbit around the Sun, just as the Earth is in an orbit around the Sun. So you'd have a 1-year period around the Sun for this parabolic orbit. You'd be phased differently than the Earth. You might be in an elliptic orbit, but you'd have a period of 1 year around the Sun. And you wouldn't be getting anywhere really that far away from the Earth orbit. If you wanted to go to another planet, then you need even more energy, so that you take this hyperbolic orbit, and when you get out to thousands of Earth radii, you'll have the v infinity, some number bigger than 0 that can carry you off to, say, the orbit of Mars. And so that brings me to this short discussion on hyperbolic orbit equation 11. This is used for interplanetary missions. So if you want to get to Mars, it is known that this v infinity value will have to be 2.95 kilometers per second. This is called v infinity, or excess speed. Not to be confused with escape speed. It's not this, because that's this guy over here. That's the speed you need to be in a parabolic orbit. Let me bring that up here. So if we plug in 2.95 kilometers per second into equation 11, along with the numbers we had before, and you crank out a value, you get 11.4 kilometers per second. That is to escape the Earth's gravity and go off to Mars. This is a huge number compared to the numbers we've seen. We looked at numbers as high as 9 kilometers per second. Now we're at 11.4. Now let's consider what we get out of the fact that the Earth is rotating. Now be careful about the rotation rate. We talk about a day on the Earth that's 24 hours. But when we talk about inertially, the Earth rotates once in 23 hours and 56 minutes. So it's not quite 24 hours in terms of the inertial rate. And so we'll use omega, another Greek letter. It's not W, okay? It's written like this, okay, and not like this. Okay. And it's called omega. And it's often used for rotation rates. We have 1 rev in, if I take 23 hours and 56 minutes, that's 86,160 seconds. And 1 rev means 2 pi radians. And I want to get my answer in radians per second. So I put in 2 pi divided by seconds. And I get this very tiny, this is a very slow rate, of course, 7.292 times 10 to the minus 5th radians per second. Sometimes we'll abbreviate radians as just plain little r, and s for seconds, sort of standard AIAA notation. Now, at the equator, the velocity would be r times omega. All right, so that's the radius and then the rate, right? So, you have if this is our radius, and then you have a rate of omega, okay, the speed out here, this velocity, v, is r times omega. Okay, so that's our basic equation for using angular rate and radius to determine this speed. So we use that, and I put in the Earth's radius and multiply by the angular velocity, omega, and I get, notice that we have kilometers here, we have radians, and we have seconds. By the way, radians are non-dimensional, and so you can drop the radians whenever you don't need it, because it doesn't have any units. A radian is just, basically the the angle subtended by the diameter of a circle. And that's basically a distance divided by a distance. So here we have kilometers per second, and we drop the radians. And so that's how we do this calculation. Notice that we have 0.465 kilometers per second. That's a fairly substantial speed to get for free. Now, of course, that's if you're at the equator. If you're down here, you get the full value of the Earth rotating. You get the R here times the omega. But what if you're at Cape Canaveral? You're up here at an angle of latitude phi. Okay, now phi is a circle with nearly a vertical line through it. And some people call it phi. Phi or phi. I usually say phi, which is both are correct. We have this angle for latitude. And so if you're up here at this point, then the R that we're talking about is really R cosine phi. Or if we take this R and project it down onto the equator, it'll be R cosine phi. So we take that up here as well. And now we have R cosine phi times omega. So instead of just R, we have R cosine phi. And so we don't get quite as much speed out of the Earth's rotation by being up there at 28.5 degrees latitude at Cape Canaveral. How much do we actually get? Let's do that calculation. The velocity gained at Cape Canaveral is taking the latitude of phi equals 28.5 degrees and plugging it into our formula. So you plug this number in here. And we already computed omega times R, which is 0.465. And now we just take cosine 28.5. And so this comes down to 0.409 kilometers per second, or 409 meters per second. Apparently Saturn V, if you look at the SPAD book, didn't quite use all of this. It might have had a slightly different requirement in terms of the azimuth leaving the Cape, and that'll give you some losses. So this is the best you can do at Cape Canaveral to employ the rotation rate of the Earth. So that concludes my discussion on the orbital velocity desired and the velocity obtained from the Earth's rotation.